Now, just to show you what this contrast transfer function looks like in a real image, here I'm showing an image that we recorded on a Polara electron microscope, a 300 kV FEG electron microscope, and the sample was graphite. Now, graphite are layers of carbon, and each layer of carbon, they stack on top of each other, and then when they pile up, they can be bent and folded in all kinds of directions. So this is the graphite material, layers of graphite that are folded in on top of themselves. This stuff is a carbon film that was used to support the graphite. And so if we take just a little piece of this image and we blow it up, you can now start to see, do you see the lines here? Each of those lines is a single graphite layer. And in an image like this, it's nice because these lines, which are approximately 3 angstroms apart, some of them appear in this direction, but in other places where the graphite is bent, they'll appear in this direction, and in other cases they'll be appearing in this direction. And so it produces a sample with these very fine 3 angstrom layers in stacks in many different orientations across the grid. As you can see, the graphite is bent up into many different possible orientations. And so when you take a picture of that, there are high resolution components, high resolution sine waves required to create those fringe patterns in all directions across the microscope. And so we took this image and we calculated its power spectrum. That's the Fourier transform squared. And so what you see in this image is a series of rings. Now these images are called Thon rings, after a person who described them. And so these are Thon rings, and what they reveal is that there's a lot of power, a lot of signal transmitted into this image at low frequencies here, and then there's a minimum here where the amplitude of the signal is very low. And then there's another band where the amplitude of the signal rises and gets high again, and then another region where there's no signal, and then another region where there is strong signal, etc. And so you have these rings of alternating presence of signal, absence of signal. And this, of course, corresponds to a CTF curve. If I were to plot a CTF curve along this same axis, what it means is that there was strong signal throughout this region, and then there was no signal at that spatial frequency, and then there was some signal at these spatial frequencies, and again passing through another 0 in the CTF, and then strong signal to another 0 in the CTF, strong signal, another 0. And so the CTF curve corresponding to this image looked like this. Of course, this axis is spatial frequency because we're in reciprocal space. And these are the bands where you get nice transfer of the information into the image, and there's gaps in between them where those spatial frequencies are lost to the image. And so we can understand the contrast transfer function as a complex band pass filter, because it allows certain bands of spatial frequencies to be transferred to the image and other bands to be lost. And so to remind you of what band pass filters are, remember this slide from the module on Fourier transforms, where we talked about that if you have an image and you calculate its Fourier transform, and then you calculate the Fourier transform of that, an inverse Fourier transform, you recover the original image with all its details. If, however, in Fourier space, you mask out many of the spatial frequencies, you essentially zero them out, and you only transfer a small band of Fourier components. When you then add those up together to try to recover, to produce a new image, so here we're adding together very many two-dimensional sine waves with their relative amplitudes and phases, but we're only using the sine waves represented by this band of reciprocal space, and all the others have been zeroed out, both at lower frequency and higher frequency. Then we get an image that resembles the original image, but it lacks both the low frequency details and the high frequency details. Some of the features are absolutely real and appropriate, but other details are missing. The EM contrast transfer function is like a very complicated band pass filter in that it transmits quite a bit of data at low frequency, but then there's a band here where none of the information is transferred. And then there's another region where the spatial frequencies are transferred, and then another zero, another transfer band, and then another gap where those spatial frequencies are not transferred. So let's go back to this picture where we wrote the formula for the contrast transfer function, sine of these terms. I want to call your attention to how the CTF depends on this term, which I mentioned was the defocus of the electron microscope. Now, one of the things about this drawing that isn't really right is that the image detector isn't at the image plane behind the objective lens. In a real electron microscope, following the image plane of the objective lens, there are additional lenses. This might be a first intermediate lens, I'll call it I1. Then there might be a second intermediate lens, let's call that I2. There could be other intermediate lenses, but for the purposes of this point, we'll just put two intermediate lenses and then a projector lens, and then finally will be the detector, maybe a piece of film or our CCD camera or whatever we're using as a detector. Then we talked about the concept of conjugate planes. Because the detector is screwed into a particular position within the microscope, and given the current going through the projector lens at any given time, the detector will be conjugate to some plane above the projector lens, meaning the same wave function that exists on this plane will also exist on this plane along the detector, except it could be magnified by the lens. But the wave function is the same. And so these two planes are conjugate. In similar fashion, this plane is conjugate to some other plane above the second intermediate lens. And then, depending on the strength of the first intermediate lens, this plane is going to be conjugate to a plane somewhere in this region. Now, given the strength of the objective lens, namely the focus of the objective lens, if you change the focus knob, it changes the current through the objective lens, and therefore the strength of that lens. For any given setting of focus, the sample plane is going to be conjugate to some plane down here, which I've written as the image plane. Now, if you want to take an in-focus image, you adjust the strength of the objective lens to cause the sample plane to be conjugate to this special plane that is conjugate to the detector, in which case your sample is ultimately conjugate to the detector and you get an in-focus image. Now, if instead you change the focus of the objective lens, meaning, for instance, if you were to turn down the current in the objective lens, the magnetic fields that it produces would be weaker, and therefore it would less strongly focus all of these scattered rays. And so instead of being focused to a point here, instead the bending would be less and they would focus to a point that's lower in the microscope, say maybe down here. And so we should erase this arrow because the sample is now, in this condition, the sample would be conjugate to some plane much lower in the microscope. But what matters is that the detector is physically mounted in the microscope. And as long as we haven't changed the magnification which changes the current in the projector and the intermediate lenses, this detector plane is going to be conjugate to a fixed plane in space within the microscope. And wherever that is, the wave function that exists in space right here is going to be imaged in magnified form and appear on the detector below. And so if we defocus the objective lens, what we're going to record on the detector is a defocused image. It will be the wave function at this position. And because this position is no longer conjugate to the sample, we get an out of focus picture. And as you can see, because the angles of these scattered rays have all changed, so too will their path length differences. The difference in their path lengths between their trajectory and the unscattered beam, all of those path lengths will have changed. And because of that, all the phase relationships that we talked about over here will shift subtly. And so different spatial frequencies will all of a sudden become visible in the image, and other spatial frequencies will be lost. And so the whole contrast transfer function will shift. For instance, if you defocus this microscope, the contrast transfer function will shift like this, changing which spatial frequencies are strongly present in the image, which spatial frequencies are lost, which spatial frequencies again are strong, which are lost. And that's why this term defocus is present in the formula for the contrast transfer function. If you change the focus of the microscope, you will shift which plane, you will shift which wave function is being imaged on the detector. Now, if you make the objective lens weaker so that the plane that's conjugate to the sample is now below the plane that's being imaged on the detector, we call that defocus, because the objective lens is too weak. It's defocused. On the other hand, if you dramatically increase the current in the objective lens, then all of these rays are going to be focused even more tightly. And instead, you will have a plane up here that's conjugate to the sample. Now in that case, the detector will image a plane below that, and as these rays continue through that plane, you'll be imaging the wave function that exists here below the point that was conjugate to the sample. And in that case, you get what's called an over-focused image. You're recording a wave function below the plane that's conjugate to the sample because your objective lens has too much current, it's too strong, and that's over-focus. And in an over-focused image, the contrast transfer function again is shifted due to that over-focus. Now, to show you what the effect of defocus is on real CryoEM images, I'd like to show you this figure from a paper from Wachu's group. In this figure, they show pictures, CryoEM pictures, of a field of icosahedral viruses. And they've circled one. So here is one of the viruses, here's another of the viruses. If you can see these are the viruses in the image. And they're plunge frozen in vitreous ice, and then this image was taken, and this image was taken with a defocus of 2.7 microns under focus. And using that formula that I showed you, you can plot the contrast transfer function for this microscope at a defocus of 2.7 microns under focus. So you see they've plotted the contrast transfer function from 1 to 0 to -1. And this axis is spatial frequency, K, as we've seen before. And here the spatial frequencies are labeled in 1/angstroms. So for instance, this is the position that carries a sine wave that oscillates up and down every 10 angstroms. This is the position that carries a sine wave that oscillates every 25 angstroms with a wavelength of 25 angstroms. And what you can see is that the contrast transfer function starts at 0, as we've explained, and then falls to -1, rises through 0 to +1, and oscillates, just as expected. Now this can be compared to another image of the same field of viruses. So these same viruses, they just image it a second time, but this time with an underfocus of only 0.95 microns underfocus. And now you can still see the viruses. Here they are. They're much more difficult to see, but they're still there. I'll erase that now. The same pattern of viruses. And if they plot the contrast transfer function for that defocus, you see that it shifted dramatically to higher spatial frequencies, in comparison to this one. And as a result, you see different features in the image. Now these icosahedral viruses are approximately 100 nanometers across, and the thickness of the shell here then is something like 40 to 50 angstroms thick. So in order to see that shell clearly, we need to have Fourier components in the image with wavelengths of approximately 40 to 50 angstroms. And if we look at this CTF curve, here at this position 1/40 angstroms, this is the position, this is where Fourier components are that have the wavelengths needed to see the thickness of this shell. And as you can see from this picture, the contrast transfer function is strong at this spatial frequency. And so these components of that image are delivered with strong contrast, and therefore we can see the boundaries of the virus. On the other hand, in this image, if we look at spatial frequencies of about 1/40 angstroms here, we see that the contrast transfer function is significantly diminished. And therefore, the sine wave that has a wavelength of approximately 40 angstroms barely contributes to this image. It's lost to the image, and therefore it's very difficult to see the edges of the viruses. Now, on the other hand, in this image, the contrast transfer function is varying rapidly. And so you have spatial frequencies here that are contributing in a negative sense compared to the spatial frequencies here, which are contributing in a positive sense. It's almost as if they were fighting against each other, where these spatial frequencies are supposed to be contributing density, they're actually withdrawing density. So their modulations are present in the image. It's just they're contributing in the opposite sense of what we would like, at least in comparison to these spatial frequencies, or these spatial frequencies, or these spatial frequencies. And as a result, the fine details in this image that are found at high spatial frequencies, they're garbled and jumbled in this image. So this image, it would be difficult to extract high resolution details. It has strong low resolution features, but it would be difficult to extract the high resolution features. Now, in comparison, in this image, there are at least out to 1/8 angstrom resolution. There's just a single oscillation of the contrast transfer function. And therefore, the high spatial frequencies are not nearly as garbled. And again, later, we'll talk about CTF correction, which is a method to flip the contributions of the spatial frequencies that are contributing in a negative sense, so they at least match with those spatial frequencies that are contributing in the positive sense. And CTF correction should be very successful in an image like this because the oscillations are not that fast. In other words, it's very likely that we could recover high frequency details from this image, even though it's difficult to actually see where the particles are. And that's because the low frequency components are so heavily damped in this image. So this puts us in a conflict. In cryo-electron microscopy, you can take pictures either close to focus, like these, in which case you can recover high resolution details, but it's more difficult to see the particles in the first place. Or you can record the pictures far from focus, like in this example image. And in this case, it's much easier to see the particles, but it'll be more difficult to recover the high-frequency details. And just to emphasize, taking pictures farther from focus, more under focused that is, shifts the CTF curve towards low spatial frequencies to emphasize the low spatial frequencies at the expense of high resolution details. On the other hand, taking pictures closer to focus, or less under focused, shifts the CTF curve to the right, helping capture the high resolution details, but at the expense of some of the low resolution components which are dampened.